Greg, I look around and I see this world that's extremely complex, and I know cosmologists tell us that at the beginning it was very simple, very homogeneous, etc. So I want to understand complexity, and I want to ask you, from mathematics, from the work that you've done, how can it help us understand what complexity is?
Well, I think complexity is a really deep, difficult question. And the way I would put it is, if you believe that the laws of physics are simple, and most scientists do, that's why they become physicists, one T-shirt, the laws of physics, then the question is, where does all this complexity come from?
Right.
Especially biological organisms. How can the world look so complicated if the fundamental ideas on which it's based are very simple and mathematical and elegant? But that's on the physics side. Now, my work has been more concerned with the fact, with taking this idea from biology, perhaps, or from the physical world, and applying it somewhere where it's unexpected to use this idea, which is in the world of pure mathematics. Mm-hmm. Because, you see, pure mathematics is like physics. People think that there are just a few fundamental ideas and that mathematics consist in long trains of thought from a few simple ideas that mathematicians can agree on, and this is called axioms, right. And this is a view of mathematics. But then there's the question, how come there are mathematical questions which can't be answered? The basic thing that I've tried to do is take this idea of complexity, which is most visible in biology or in the physical world, and use it to try to understand a famous result on the limits of mathematics, which was proved by Gödel in 1931. And I've been obsessed with this result of Gödel.
Which is what? Tell me what.
Well, Gödel in 1931 came up with a result which was very shocking for mathematicians, which says that no finite set of axioms. The normal notion of mathematics that a lot of mathematicians will tell you they believe in is a creed, is that in theory all of mathematics is like Euclidean geometry. You have a finite set of postulates or axioms, and just applying the laws of logic you can in principle get everything.
Right.
Okay, the only problem is that Gödel in 1931 shows that you can't even get 1, 2, 3, 4, 5 and addition and multiplication. I mean, you can't get just what's called arithmetic, which is just the properties of the whole numbers with addition and multiplication, which is a very simple mathematical theory. You can't even get all the truths about 1, 2, 3, 4, 5 and addition and multiplication.
What do you mean by you can't get?
From any finite set of axioms.
So any finite set of axioms you can't absolutely prove.
You can't prove everything. It's called an incompleteness result because it says that any mathematical theory for 1, 2, 3, 4, 5 addition and multiplication is incomplete. Any mathematical theory for elementary arithmetic is incomplete. Whereas the idea at that time when Gödel did this work was that we knew the postulates for arithmetic, that all mathematicians learned them in the cradle, and just applying the laws of logic, which were also very well known, a machine could in principle deduce all possible conclusions. And this would be every truth about 1, 2, 3, 4, 5 in addition and multiplication. And Gödel showed it won't work, not just because the axioms that people knew then were bad, or because the logic used then. It would never work because no set of axioms and no logic could give you all the truth about the whole numbers and addition and multiplication. Now, but let me contrast this with another situation, which is Euclidean geometry. Euclidean geometry, you can do that. With Euclidean geometry, there is a set of axioms which you can show gives you all the truths about Euclidean, all the truth and only the truth about Euclidean geometry. And given any statement in Euclidean geometry, there's a beautiful result of Tarski, which is sort of the opposite of Gödel's result. Gödel says no mathematical theory can give you just the truth and all the truth about the whole numbers, about elementary arithmetic. But Tarski has a positive result, which says there is a theory and there is a that gives you all the truth and only the truth about Euclidean geometry. And in fact, that gives you a way for any assertion of Euclidean geometry to prove it's true or to prove it's false. But this cannot be done for... So Euclidean geometry, in a way, has finite complexity. Yeah. We can understand it. We have a mathematical theory for it. But 1, 2, 3, 4, 5, addition and multiplication sort of escapes mathematical reasoning because no matter how many axioms and how many principles you use as the basis, there will always be truths that cannot be reached starting from those axioms. Yeah. So it's not just that the that the particular axioms that mathematicians were using then, called Peano arithmetic, fail because they don't really include everything. It's that no finite set of principles is enough. In other words, the way I view it is that 1, 2, 3, 4, 5 addition and multiplication, simple as they may sound, that's really a very easy part of mathematics, is actually infinitely complex.
Wow. So what are the implications of that for the complexity of the world?
Well, what it shows is it's a first step. I think a big intellectual problem is to understand where all the complexity comes from in the world.
Right.
And how you can have simple laws of physics and get a very complicated world. And another big problem is to know where all the complexity comes from in biology. Well, another big problem is to have a mathematical theory for biology. Mathematics does not apply very much to biology. There's this big problem that mathematics is very helpful in physics and not very helpful in math. And why?
In biology.
In biology. And the reason is, people say, because biology is very complicated. It doesn't really, simple equations and mathematical ideas don't apply. So that's a very big challenge for mathematics. This is the century, the previous century was the century of fundamental physics. This is the century of molecular biology. Does that mean mathematics is through because mathematics cannot contribute to this, that there will not be a theory? So I cannot answer these questions, but I think I can make one little statement. This is only a lifetime of effort. This is all I can say about this, which is that pure mathematics is actually even more complicated than biology because it's provably infinitely complicated.
And yet mathematics...
So in that sense, pure mathematics is much closer to biology, which is messy and complicated, than it is to theoretical physics, where people still believe that a few equations give you a theory of everything.
Yeah, but mathematics sit at the foundation of physics.
Well, yes, that could be disturbing.
And if you're saying now that mathematics it's impossible to have a complete mathematics,
a theory of everything for all of mathematics.
A theory of everything mathematics. What does that say about the nature of the world or the nature of complexity?
Well, it says that the nature of the mathematical world is that it's infinitely complicated and we're never going to have a theory of everything. That doesn't mean that we're not going to ever have a theory of everything for physics. Mm-hmm. They're I think they're separate problems.
Yeah, I understand.
Even though math is the basis for theoretical physics. Right. I think they're separate problems. But what this does, but you're right to react like that, because on the face of it, this sort of gets rid of the idea that mathematics is the basis for rational thought, and that a science progresses to the extent that it uses more and more mathematics. But now if you say that mathematics has problems, what happened with this whole view? And that's... So the answer, you're not going to be surprised, therefore, to hear that mathematicians tend not to like what I'm saying and my work because it doesn't fit in their way of viewing their lives and their own subject. But physicists tend to feel comfortable with these ideas. And part of the reason
We're not here to make people happy or comfortable.
We're
trying to find the truth.
We're trying to find the truth, right, exactly. And very often, to find the truth, you have to question everything that people believe in general. Well, you don't have to do that. You're sometimes forced to do it against your will. I mean, my goal in life was not to annoy my colleagues. Would be a very stupid goal. My goal was simply to understand what was going on, and I just didn't care whether it annoyed them or whether everyone loved it. That I didn't ever thought about.
And what's going on is mathematics is just unable to have a complete system.
Well, yeah, and my tentative conclusion is that pure math is more like biology in the sense that pure math is infinitely complicated. Biology is just very complicated, but finitely complicated. But on the other hand, I would say that I believe that pure math is a little more like physics than mathematicians think. Because, you see, what mathematicians thought is they had absolute truth. That pure math, a proof either is absolutely correct or it's garbage. That only mathematicians can touch absolute truth. And empirical sciences don't get to that, right? And even less economics, the courts. Okay, but if you say that no mathematical theory can give you everything, there are no finite set of principles we can all agree on to use as a basis for mathematical proofs, that means that mathematics really ends up being in the air, because then the question, it seems to me, is, well, you have to keep adding principles clearly then. And that becomes a matter for dispute. What if because you can't prove them, so on what basis do you add a new principle? You add it because religious faith, you add it because of computer experiments that suggest something. I mean, it becomes a question of belief, of evidence which is not absolutely watertight, because that would be a proof. You can ask for proof.
So what does that mean about the complexity we see in the world?
Well,
is it mathematically based?
I don't know. All I know is that there's a lot of complexity in the world of pure ideas, in the world of pure mathematics. That's what I've concentrated on.